Your Royal Highness, fellow Nuffield scholars and honoured guests, good afternoon. In my day-to-day work, I'm involved in the management of over 12,000 acres of productive land and approximately 5,800 acres of land managed to incorporate all aspects of day-to-day land and estate management, together with a further 6,200 acres as a retained advisor for property, agricultural and environmental asset management. Annually, I advise on a single payment scheme, cross-compliance and agri-environment schemes for over 22,000 acres. As a land manager, I was drawn to complete a Nuffield Farming Scholarship through the determination to understand the land that I'm entrusted to manage. It was increasingly apparent that much of the location reference data being collected on farms through precision agriculture offered a vital source of information for both agriculture and land management. But whilst information was being collected, it was not always being utilised. My studies took me to the 2013 European Conference on Precision Agriculture held in Spain, where I met some of the world leaders in precision agriculture: the Netherlands, France, Germany, Australia and New Zealand. I also looked at other related industries, such as forestry. I would like to thank the John Oldacre Foundation and the Nuffield Scholarship Trust for the opportunity to complete the scholarship, together with my family and work colleagues for their support during my travelling. Today I will look at three key areas from my study: data management, the environment, and the concept of precision land management. There is a significant problem on the horizon for agriculture and rural land management: the need to feed a growing population on a fixed supply of land whilst managing the environmental impact on that growing population. An industry-led support titled The Best Use of UK Agricultural Land, published in June 2014, states that by 2030, the UK could require an extra 7 million hectares of an additional land to meet the need for food, space and renewable energy. One way to achieve this is to increase farm productivity whilst reducing negative environmental impacts through sustainable intensification. Global positioning systems provide location information. The type of GPS correction signal determines the accuracy. Elevation data, which can be collected using the most detailed correction signal, is very useful and perhaps the most underused. Remote sensing includes cutting-edge technology such as MEMS sensors, which form part of a research project I saw at the University of South Australia. These sensors were potentially capable of providing data such as soil moisture and soil nutrients in real time from the field, costing only $10 per sensor. We can produce a large quantity of data, as we have seen from Andrew. So the question is, what do we do with all of this data? We need to analyse the data first through geographical information systems or farm management information systems. We then need to apply our knowledge to find out what has caused that variability and what action is required going forward. Crop outcomes are not just affected by one variable, but a complex relationship between different variables. And this makes analysis, interpretation, and knowing how to manage the crop a relatively complex process, which needs to be supported by computer modelling. At the University of South Australia, I was shown how modelling was used for 3D tillage simulation to simulate the effectiveness of cultivation machinery. The potential reaction of each soil particle to a cultivation operation was modelled to simulate the outcome of that operation without even having to set foot in a field. It became apparent to me that modelling and simulation provide the key for interpretation and practical application of large data volumes. In the Netherlands, farm elevation data is used to design and model land drainage schemes using software that can simulate water drainage following a rainfall event, as well as cost a proposed drainage scheme. In Australia, elevation data was being used to simulate the risk of frost damage within a field. Simulation has an important role to play in the analysis and utilisation of agricultural data. Data can be modelled based on data obtained through a growing season to provide projected yield outcomes. While staying with Peter Kaylock, a fellow 2013 scholar from Australia, he introduced me to his agronomist, Ian Delmenico, who was advising him using an Australian crop modelling system known as Yield Profit. Yield profit is used to assist management decisions through a season. Growers or their advisors enter their inputs during a season, and the system reports on yield potential, showing the impact of sowing time, nitrogen management and irrigation on crop yield. It provides real-time assessment of crop yield potential throughout the growing season, accounting for climatic conditions. I've not come across anything similar in the UK, but the development of such models and cropping simulators to utilise the vast amounts of data produced by precision agriculture will be essential in assessing the yield potential of land and potential return against inputs and the environmental impact. Whilst precision agriculture has environmental benefits resulting from the application of inputs in the right place at the right time at a farm level, there is also a need to consider the environment on a wider landscape level and target some conservation practices such as buffer strips to reduce soil erosion or site-specific actions to reduce leaching to contribute to soil and water conservation through precision conservation. Within UK agriculture, we recognise the importance of protecting the environment, ecosystems and the services it provides, which underpin agriculture, such as nutrient cycling, soil formation and pollination. Pollination alone is estimated to be worth 430 million a year to the agricultural economy. We therefore need to monitor our impact. More research is required to understand our interaction with ecosystems and what opportunities there may be to enhance ecosystem services such as pollination. At the University of South Queensland, I saw a bee activity recorder which was used to monitor bee activity, temperature, weight, and it consisted of smartphone technology, data loggers and a processor. From my travelling, it was clear that New Zealand farmers are very good at monitoring their impact on the environment and self-regulation. For example, the Foundation of Arable Research have developed a farm software self-regulation tool that models nutrient flows and can be used to assess the risk of nutrient leaching. This has helped towards reducing or limiting government regulation. Craig Mackenzie, a 2008 Nuffield scholar from Methven, has on his dairy farm an eddy covariance tower which helps him to monitor CO2 emissions and mitigation on the land, and a lysimeter used together with soil moisture probes to monitor leaching risk. A year ago today, I visited Sundown Valley Farm located on the northern tablelands of New South Wales. It extends to approximately 20,000 hectares, rearing over 40,000 head of cattle each year. The farm participates in the Pastures from Space system, which uses daily satellite imagery to measure pasture cover and predict pasture growth. The system can provide pasture growth rate maps and food on offer rate maps for individual paddocks. Agronomists at Sundown Pastoral use the data to determine which paddocks will be rested to prevent soil exposure and risk of soil erosion, and which paddock will be grazed. Sundown Valley Farm was an excellent demonstration to me of the utilisation of precision agricultural technology for land management, which balanced the production needs of the cattle enterprise and the environment. Mark Branson, a 2005 Australian scholar, was farming using precision agricultural technologies. His passion for managing the environment to enhance his crop production showed me that increased production and enhancing the environment can go together to achieve sustainable intensification. My visit to Calder Estates Forestry in Scotland, where they manage over 60,000 hectares of woodland, using GPS, remote sensing and geographical information systems, show me that these technologies apply to a range of land uses with the same benefits, and across a landscape they can be combined to form precision land management. Armin Werner at Lincoln Agritech, New Zealand, highlighted that sustainability cannot be achieved on one farm alone, but needs to be considered across a landscape, and therefore is part of a concept of a wider remit of precision land management. Rural land and asset management. So what does this mean in relation to my day-to-day work? Our current land classification maps for the UK rely on data collected in the 1970s and has been classed as provisional for the last 40 years. Whilst being a useful reference point, I believe that we should have an updated system of land assessment and classification. I believe that farm data such as soil mapping, nutrient mapping, all provide valuable information for making informed decisions about land purchases and lettings, where the data is available, and should be used to consider the productive potential of the land. You wouldn't buy a house without a structural survey. In my day-to-day work, I have been converted to using GPS for land measurements, and we have recently invested in a GIS mapping system capable of using GPS data, which I'm sure will be very useful when I have to map all my customers' ecological focus areas next May. Data from precision agriculture can also be used to help administer land use on let land or land managed under contract farming arrangements to ensure nutrient status of the land is being maintained. Farm data will also be very important for regulatory compliance. If operators input in-field tasks correctly into the sprayer or the fertiliser in-cab screen, it should provide a day-to-day record of spray and fertiliser applications without having to ring your advisor the night before an inspection. Trust me, I've been there. It's all about farm data. It has a value as long as it has an application, and data records should be maintained as historic data can be used to identify trends in previous cropping. I feel that data produced from the land should remain with the land, so if you sold some land, you would transfer that data across to the purchaser, and similarly if you surrendered land on a tenancy. You wouldn't take on a business without seeing the previous year's accounts. Data ownership is an important issue that needs to be addressed. There is no option but to utilise data within agriculture and land management to improve practices, adapt and become more efficient, and monitor our impact on the environment. Thank you.